to talk a little bit, just a little bit more about the dot product, and then about the cross product. Introduce the cross product in just a little bit of different way from the way the book does it. In another video, I talked a bit about dot product and projections, but I focused on what the book very reasonably calls the component. The component of A in the direction B is, well, what's the picture? I've got vector B, and then I've got vector A here, and I just want to know how much is A going in the direction of B. And so two really huge features of that is that that's quantities of scalars, just to how much. And the other thing is that it doesn't depend on actually what B was in terms of magnitude. B could be out here, B could be here, B could be here. It's just the direction of B that's important. I guess the third thing to note is that it does have a sign to it. If A was like this, and they were generally opposite, I want to record the fact that A is generally going opposite to B. And so it turns out that that's just equal to the dot product of A with B, which now that would include magnitude information for both A and B, and we don't want magnitude information for B, so we just kill it off. We just divide by the magnitude of B. Okay? And so that's a scalar component of A in the direction of B. Now, sometimes we really want the actual projected vector. We want to take this thing and actually squish it down and leave it as a vector. And we want this vector not just a measure of how long it is and whether it's agreeing with the B direction or not, which is what this was. Well, that's quite easy. We just do a two-stage process to create the projection proj of A in the direction of B. And you know, the book, I can't remember if the book uses A and B in this role or different roles, but you know, it's good to get used to not being counting on the letters being in certain places. This information is still really important, because that's basically the length of the thing. It's assigned length. And so I'm going to take that quantity, and now I want to use that to create a vector in the right direction. So this is basically the magnitude information, and it has a sign as well. And so I just want pure direction information. Well, how do I make a pure direction information? I turn B into a unit vector. So I'm going to take B. Now if I multiply these guys, that would be all wrong, because part of the point of dividing by the magnitude of B here was to kill the B magnitude information. If I multiply this scalar times this vector, it's going to bring back the B magnitude information. It's going to take this thing and scale it by the length of this guy, which isn't right. But if I make this into a unit vector first, then I've got a unit vector which is pure direction information. Its magnitude is 1. And then I multiply it by this number. The magnitude's going to be right. It's going to be either in the direction of B or opposite, depending on whether this scalar is positive or negative. And so we're going to get the right projection. Okay, so that's the vector projection of A onto the direction of B. And we can, that's actually rather nice. There's one very nice feature of that, is I can collect all the scalar part together. It's just a certain scalar times B. And this guy is a magnitude squared. That means there's no square root on the bottom. This is actually just, you know, B1 squared plus B2 squared plus B3 squared, for example, in 3 dimensions. And that can be a huge deal. It might not seem like a big deal right now, but if this goes into like some sort of integral formula and there's variables and stuff, square roots can be a huge pain, and it's nice to not to have them. So in some ways, this projection is a nicer gadget, even though as a vector it's a little more complicated. Okay, so you get some practice with that. I just wanted to lay out the idea of that. Now, the other thing that we're jumping into is the cross product. And I have to say, in a way, this is not exactly how I want the course to work, but I'm not sure exactly how to do it and have a finite amount of time available. There's a beautiful connection with between the cross product and determinants, and we're going to see a little bit out of the book, but we're going to have to go further with the determinant investigation before we really see nicely how they match up. And so unfortunately, I would have liked to get further with the determinant investigation before we started cross products, but I don't see any way to do that without just pushing stuff off too far. So we're going to have to take a few things on faith as far as determinants go, in particular the formula for a 3x3 determinant, which we will totally derive from first principles with our investigation. But it's going to give away a little bit of a punchline, but it's not a big deal. Okay? So I'm going to turn things around a little bit from the way the book describes things. And so it means the book is really, it's going to be good to read that as a complementary source. It's not different information, it's a little bit of a different order. So here's the data that we have. Let me check my time. Okay, the data that we have is two vectors. Let's say u and v in R3. And for the first time, it's going to really matter that it's in R3. This does not work. The cross product itself does not work in R3. There's similar ideas that work in any dimension, but they're more sophisticated than we want to do. So there are two vectors in R3. And what do those determine? And what kinds of questions could I ask about that? Well, we've gotten used to the fact that it's a pretty good idea to draw the parallelogram that they form. If we're interested in summing the two together, that's a good idea. In 2 dimensions, we saw that we've been seeing in the determinant investigation that those make a parallelogram with an area that we might want to calculate, and the 2x2 determinant has something to do with that. And we're investigating that right now. Well, in 3 dimensions, they do form a parallelogram with an area, so that has some sort of area to it. But it could be sitting in all kinds of different ways, different attitude, as like a pilot would say, in space, a different way of sitting in space. And we'd like to record all that information. So one example of that is one place we're going to use this is if I have like some fluid flowing through all of space, and I make a parallelogram-shaped net, or filter or something, like a mesh, I'd like to know how much fluid flows through that mesh. If the fluid is flowing basically perpendicular to the mesh, I'm going to get a lot of flow through. If that's like a fish net, I'm going to catch a lot of fish. Even if I don't change the area of that net, if I change the attitude of it and the fluid is flowing by it or parallel to it, I'm not going to catch any fish. So it makes a huge difference what the attitude of the thing is. So the nice thing is that that's magnitude and direction information. The magnitude is the area, the direction is the attitude, but it's a little bit weird. We're not used to talking about direction of a plane. What we have is the technology for talking about the direction of a line or a ray, really, and that's a unit vector or some sort of vector information for magnitude and direction. So we're going to actually be able to put all this into one vector. So here's what we're going to do. We're just going to say that u cross v, our goal is to create a vector whose magnitude is the area of the parallelogram spanned by u and v. So that tells us something about its magnitude. Now, one really important thing is it's a vector. I'm going to give you a formula for that magnitude, and you don't want to memorize that is the cross product, because it's not. It's only part. It's only the magnitude of the cross product. Okay, so that's only part of the specification. Its magnitude is going to end up being the area of the parallelogram spanned by u and v. Okay, and so that already you can see there might be a connection with the 2x2 determinant stuff, because it's talking about the area of the parallelogram. And which is, well, I want to see something about its direction. Okay, if it's a vector, let's see, if I have a plane, is there some natural direction I can pick that's going to be a reminder of how the plane sits in space? Think about that for a second. Is there some way to attach a line or a ray or an arrow naturally to a plane that's going to move around with the plane and be enough information to tell me how the plane's sitting in space? Well, if I make that line perpendicular, then that's going to be enough information. Because if I give you this line, you know, oh, you mean this plane is perpendicular. If I give you this line, oh, you know it means this plane. Those guys share the same information, the attitude of the plane and the direction of the line. So that's exactly the kind of direction information that a vector can encode. So u and v span a plane as well as a parallelogram. And I'm going to make sure, my goal here is to create a vector u cross v that's perpendicular to that. And that's going to give the direction information. Now, here's a tricky thing though. If I take u and v, let's say this is u, thumb is u, and forefinger and index finger is V, then I could either choose a vector here with the correct magnitude, or I could choose the exact opposite. And so far I haven't specified which one to pick. And I want this to be a definite choice. Well, what we're going to do is we're going to kind of choose, we're going to choose systematically, but there is a certain amount of an arbitrary convention to it. We're going to use what's called the right-hand rule. Okay, so in fact I should start using my right hand. Here's my right hand. What we're going to do is we're going to say if U is the hand itself, and V is the fingers, then the way the U cross V vector is going to point is going to be my thumb of my right hand. Don't use your left hand. It's called the right hand rule for a reason. And so we're just going to put down, it's hard to write down in words, satisfies the right hand rule. Let's check our time. Okay. So that's going to be something that encodes all this information. So it's going to end up being like this. U cross V. Let's check the right-hand rule. U and then V. Now here's the tricky thing about the right-hand rule. When we use this version of the right-hand rule, here's U, here's V. I'm really thinking of this version of V over here. This works best. The right-hand rule, as I described it, U and then V. It's easiest to see it if you put them tip to tail, like you're going to add them. If you're there tail to tail, it can be a little confusing. But here's U, then V, and then U cross V is pointing in the thumb direction. And that's going to encode, its magnitude is supposed to be a proxy, kind of a code for the area of this guy. Its direction reminds us of how that thing sat in space. And the right-hand rule tells us something. Well, let's see. Does that really tell us any interesting information? There's an arbitrariness to it, but let's think about it. If I switch U and V, with each other, then I'm going to end up going in the opposite direction. So that's a really interesting thing. It tells us algebraically that this is what's called an anti-commutative or skew-commutative product. There's a minus sign here. When I flip the order of two vectors in a cross product, you get a minus sign. That should look familiar from the determinant. It looks like, oh, maybe this is really secretly sort of saying this is a signed area, and that's really what's going on here, is that secretly there's some signed area information. And it's really coming in. The deep reason why this has to be true is for the same reasons that we were sort of discovering why signed areas are important in the determinant. So let's just go a little further with this before I have to stop at the 15-minute limit. Got 2 more minutes. So the magnitude of a cross product, is there a nice formula we can have for that? Yes, if we're willing to look at angles and trig. Let's say the angle between these vectors is theta. Then I would just want to look at the area of parallelogram. And this is the first time I've actually suggested trotting out that version of the formula. So I'm going to put that just in the plane of the board. It's base times height, so let's say make U the base. Drop a perpendicular. There's a right triangle with that angle theta, and this guy is magnitude of V sine theta. Now this should look very familiar. It looks like the dot product, except with a sine instead of a cosine. And the big mistake people make is thinking that is the cross product. That's the entire deal. Oh, what's the big deal? It's just sine instead of cosine. It's just like the dot product. It's really different from the dot product. It has a very different role. It's true that the magnitude is proportional to the magnitudes of the two factors, and there's a sine theta instead of cosine theta. But it is a vector that goes in a certain direction that's perpendicular to U and V, that satisfies the right-hand rule, and its magnitude happens to look kind of like the dot product, but with a super important difference that it's sine instead of cosine. But this is still going to be a very interesting, important thing. Now, this is sort of geometric introduction to the cross product. What it doesn't bring up is there an algebraic formula for it? That's what the book starts with. That's where it connects to determinants, and that's where we still need to do some work. But I'll let you get most of that out of the book.